Okay, so last day we talked about different types of polymers and different ways you can classify them or explain them. So we'll look at the structure today and then the properties. Hopefully we get into 1.6 today. So linear is exactly what it sounds like. These are polymers that are in straight chains. And again, I'm just kind of going over what we did last day. Um, Linear polymers, long straight chain polymers, usually alkanes or single bonds. Just like they sound, they are linear or in a single chain. These can be very, very long. A good example of a linear polymer was polyethylene or high density polyethylene. Then we talked about branched polymers. This is exactly what it sounds like. You can think of like a tree with branches, right? So a branched polymer has branches or carbon chains that stick off of the main chain. And an example of this is low density polyethylene. Um, the reason that linear are high density and branched are low density is because of the shape. The branches make it hard for the polymer to fold and pack itself together. So it creates space in that molecule, which lowers the density. Branching, I mentioned this last day, but branching can also affect physical properties, which any of you guys getting into chemistry 2420 will learn about viscosity. That's the thickness of a polymer, and elasticity. So you kind of like the flexibility of the polymer, but you guys don't need to know this slide, but it is an interesting fact or phenomenon. I was reading in the news the other day, actually, about I don't know where he's from, but they've this gentleman has come up with using plant-based carbon chains to make polymers like plastic bags that are completely biodegradable, which would be really, really good for our environment. Aman asked a really good question. Yeah, basically multiple choice definition, not definition like explaining, but multiple choice. Could be fill in the blank or multiple choice. You in this course, you won't really, and Aman, you had me last semester, you notice that I'm not going to get you to write big giant paragraphs. And Aman, I got your email about the cross-linking and network. I'll cover that again today as well. But for anybody wondering about tests, this would be like multiple choice or fill in the blanks. So cross-linked polymers, these, again, these are pretty easy to kind of memorize because their names explain exactly what they are. Cross-linked polymers have side chains that link to form like a network. So you could think of cross-linking as like, these are my polymer chains, and there'd be like branches that connect them. I mean, you could think of it like a spider web or something like that, but I don't want you to think that it looks like a spider web exactly. But there are links between the long polymer chains. So adding cross links between polymer chains can make it more elastic, so you can stretch and bend them. It also decreases viscosity. That's the resistance to flow. In chemistry 2420, you'll learn a lot more about viscosity. But a good way to think about viscosity is like the difference between honey and water. Imagine, putting honey in a glass and water in a glass and then trying to pour them out. The honey resists flow. It's very viscous and thick. So when you cross-link a polymer, it kind of makes it more like, I want to say oily or thick, like honey. Again, you'll learn a lot more about this in 2420. This picture is probably the best picture I could give for cross-linked polymers. Oh, and Aman, yeah, I mean, Glue would be very viscous. Yes, that's a really good good example. Cross-linked polymers. Somebody might have had a question there. I just heard a mic. But an example of this is vulcanized rubber. This is car tires. So think about the tire on a, I say car, and in Canada we call everything a car, but I mean your vehicle. That type of rubber is very elastic, so it can stretch. You know, you can fill it with air or let some air out, and it's kind of, well, like exactly like rubber, an eraser, a car tire, and it's because of the cross links. So you can see, whoops, sorry, I have my chains, but they're linked together or connected. In the example of vulcanized rubber, the links are sulfur, but it doesn't have to be sulfur. It could be carbon as well. You don't need to know anything about car tires, don't worry. But I just wanted to give you an example of that type of polymer. And the last polymer is probably the most complicated in terms of, you know, what it looks like. A network polymer is extremely highly branched and cross-linked, very many numerous interconnections. Actually, this is maybe more like the spider web I was talking about before. So the molecules are very complex. They have many, many branches and many cross-linkings that connect them together. An example of this is Bakelite. And just give me 1 second here. I made these notes a long time ago. Just trying to see like what type of product you would see Bakelite, and I don't think it's used as much as it used to be. Bakelite is so densely packed with molecules, it actually kind of resembles jewelry. It can look like you know, a diamond or a gemstone, which it's not. It's what we would call a plastic, but it's very dense. It's I'm looking at the things I'm looking at are so old, like an old telephone. So even before, way before mobile phones, like an old telephone, the outside plastic was very hard and it was made of bakelite. So these polymers, because they're so highly branched and cross-linked, they're very dense. They're not very flexible. So these types of plastics would kind of break or shatter. Yeah, actually, yeah, Yasmin, that's a really good way to think about it. It does look like a honeycomb, which is, yeah, a really good example. So like a bee's hive or honeycomb, very complicated connections. Pretty interesting. I'm just on the Wikipedia article looking at Bakelite, and I mean, I don't think it's used very much anymore. It was used a lot in like World War I for like telephone technology, radios, but I don't think they use it very much anymore, but that's a good example. For anybody who hasn't had me before, I link to these guys a lot. I won't click on this link now because, you know, I'm on Zoom and I don't really want to load a YouTube video. But these guys, the Crash Course, these are fantastic. Well, it's actually like one guy on in front of the camera, but really fantastic tutorials. So, and they're very entertaining. They have a lot of good animations and visuals. So if you ever want to check these guys out, you can just go to Google or YouTube, sorry, and just type in Crash Course Chemistry, Crash Course Physics, Crash Course Accounting. I mean, they do everything. Really cool. And a little bit more entertaining than Khan Academy, if you guys have ever been there too. Okay, so What I want to do, I hope that made some more sense. What I want to do with you guys today is go over some types of polymers, and I'm going to give you a couple of definitions here that are really wink, wink, wink important. Thermoplastics and thermoset. Wink, wink, wink. It would be very, very good for you guys to know the difference between them. So let's get into that. I'm going to give you some examples of plastics, talk about thermoplastic, thermoset polymers, and some examples of them. Pretty easy. This is a pretty straightforward chapter because there's no math. It's just kind of memorizing terms. Okay, so because of the range of properties, I mean, this goes back to why carbon is like the coolest chemical on the periodic table, or the coolest element. It can make millions of molecules, organic compounds, polymers, plastics, oil and gas are made up of it. I mean, it's everywhere in your life. If you have polymers in your pocket right now, if you have a cell phone, you guys are obviously looking at a computer screen. So, I mean, you're staring at polymers. It has literally changed our lives. So polymers can be natural. So things like DNA, biopolymers, so things that you might find like cellulose or things in trees and plants, they would be natural. Oil and gas would be natural. I don't know if I would call it a polymer, but some of the long carbon chains you could call a polymer, and they're all natural. But there's also synthetic ones, and that's kind of where plastic comes from. Plastic doesn't exist in nature, not in the sense that what we think about plastic. So they're all made in the lab. You do not have to memorize. Like, I'm not going to ask you to give examples of natural polymers, but you should know, or it's good to know just some of the examples. So cellulose, this is, what makes paper. It's found in trees. Wool and silk are natural polymers. Natural rubber, you also find in trees. It's kind of gummy. Amber, another, again, trees. You'll notice a lot of these are found in trees. Wool and silk are obviously from animals. These are just some examples. Now look at the list of synthetic. There's well, not millions, but hundreds of synthetic chemicals, synthetic polymers we use. You'll notice that these are links. So if you open up the PowerPoint, if you're curious, you can click on any of these and read more. Again, you do not need to know anything about these synthetic polymers, but I just wanted to give you some examples. So nylon, right? A lot of your clothing, anybody who wears like mixed type of fabrics like cotton and nylon is a synthetic, and synthetic, guys, just means made in a lab. That's all that means, is a good example. Polyvinyl chloride, PVC, people have used in the past in piping or pipes, in plumbing. I guess I should say plumbing. I say used in the past, it's still used today as well. Polystyrene is like styrofoam or packing peanuts. What's another one? Neoprene. It's used in wetsuits. It's a very good waterproof but very flexible fabric, or I guess I shouldn't call it a fabric. It's a polymer, I guess. So these are just some examples of polymers. Again, you don't need to know anything about them. All right, this is where it gets important. I'm winking right now, okay? So a thermoplastic. You will definitely need to know the difference between thermoplastics and thermoset. And there's really one big difference between them. So a thermoplastic, think about the word heat. Okay, so whenever you hear the word thermo, like thermometer or thermochemistry, you can think of heat. It's a polymer that becomes pliable. And if you don't know what that word is, it's like flexible, moldable. Like when you heat up metal and you can shape it, they become moldable or pliable above a certain temperature and then become solid when you cool it. So a thermoplastic is really useful because what you can do is you can heat up this polymer, put it into a shape, like it could be a lunchbox, a cell phone case, and then let it cool. And when you cool it down, it will turn to a solid. Okay, that's it. That's you. This is what you need to know. So it becomes moldable when heated, and then will go back to a solid state when you cool it. And I'll explain why that's important when I get into the other one, because a thermoset polymer cannot do this. The thermoplastics, they have a lot to do with intermolecular forces, which allow them to be remolded. This is, again, from CH1120, talking about intermolecular forces. Don't worry, we're not going to get too much into intermolecular forces in this course, but the reason they can do this is because of intermolecular forces. You know, like hydrogen bonding, London dispersion, or polar. But don't worry, you don't need to worry about intermolecular forces. We already did that last semester. So thermoplastics, things that can do this, like polyethylene, polystyrene, PVC, again, talking about those pipes. You heat up this polymer, shape it into a cylinder, let it cool down, you have a pipe. If you reheated it again, you would melt it. So these are polymers that you imagine if you've ever left something plastic on a hot stove, they kind of melt. That's what these thermoplastics are. So thermoset plastics, what are these? Well, thermoset plastic is a material that, and I'll explain what this means in a second, it irreversibly cures. So the curing process is kind of like this heating and cooling process. But the big thing here is that thermoset plastics, they do not melt or reform upon cooling. You cannot melt them and shape them. When you heat them up, they completely break down. Okay, the cure is your first heating cycle. So you heat it up, you could have a chemical reaction to kind of make this type of plastic. But once it's made, it is called set. And in English, the word set means like, I mean, it's formed, it's in its final form. So once you've taken a thermosetting plastic and, you know, made your product, when you apply heat again, it completely breaks down. I don't know if this is a good example, but it's a good way to think about it. It's like a plastic bag. If you, like a Ziploc bag, saran wrap. If you took a plastic Ziploc bag and put it over a candle or, a lighter, and you heated it up, it would completely break down. It would go away forever. Like it would just, combust basically. So to summarize, because you will see this question, a thermoset plastic can be heated and molded over and over. Okay, you can heat it up, make it change its shape, cool it down, and repeat. A thermoset plastic is set once you've done your chemical reaction, and if you heat it again, they break down. They cannot reform. All right, does that make sense? Oh, well, we got lots of time left. This is good. I won't go too crazy today because it is like a late class. I'm sure you guys are busy, but maybe we'll do a little bit more. And yeah, as Harold says in the chat, one can be molded and the other breaks. That's a really simple way to put it. Somebody's microphone keeps coming on. Does anyone have a question? But yeah, Harold, yeah, one can be heated and molded over and over, and the other one breaks or is destroyed upon heating. Ooh, Abdul Halim has a good question. Why is plastic so hard to be recycled? That's a really good question. It probably has to do with this property. A lot of recycling, like think of aluminum. Okay, when you take an aluminum can and heat it up, or glass and you heat it up, that would be like a thermopolymer or a thermoplastic, sorry. When you heat up aluminum or you heat up glass, it will melt. You can shape it again and then cool it down. It becomes solid again. So when you think about plastics, if you heat it up, it might not be able to be reformed. So a lot of plastics that we use, like plastic bags, are thermoset. So when you heat it again, you can't really get that product. It kind of disappears. It's a really good question. And the other answer too is aluminum is an element. It's a metallic element. So, you know, we can heat up metals, you know, shape them, cool them down. That's how people make knives and aluminum pots and pans. Glass is made up of one compound, silicon dioxide, heated, easy. Plastics can be made of many, many chemicals. So again, very hard to recycle that because when you heat it, those chemicals can be destroyed. That's a good question. I don't know if I'd ever be able to find this. If I can find this video, I want to show you something. I think you guys will like this. I'm just going to see if I can find a video to show you because it is really cool. Okay, I normally don't show YouTube videos, but I think you guys will enjoy this. So I'll share my screen in a minute. I just want to get the video up on YouTube. When I was in university, I had a really, really interesting professor. He was a British guy, and he showed me, he did like a demonstration. And he showed me what happens when you put styrofoam into acetone. And I just want to show you, I think this video, it's pretty cool. Oh, this is good because this is only a minute long. Okay, hold on, let me share my screen. I get nervous showing YouTube videos because you never know what you're going to get, right? I mean, my brother has children and they like to watch YouTube, and he'll leave the room for like an hour and come back and they're gone on into some crazy YouTube spiral. So anyways, this video looks pretty good. So this is styrofoam, polystyrene, and in this plate, which looks like an IKEA plate, is acetone. So acetone is a ketone. Remember ketones? And it's a very simple chemical compound. It's a very good solvent. So look what happens. I got the sound off, and you could put so many cups in here, like it's crazy. So excuse me, sorry for coughing into the mic. What's happening is the acetone is a solvent, and it's breaking the polymers in polystyrene down. So it's breaking the chains. And when I say breaking, it's just kind of dissolving, breaking bonds, and it basically breaks completely down. It's like the reversal of polymerization. Pretty cool. And when I did this, when my professor showed me this in class, he did like 10 or 12 styrofoam cups. It was really cool. Looks pretty gross, doesn't it? Ugh. Anyways. All right, I won't show you that. There you go. Anyways, pretty cool, isn't it? Pretty crazy. So guys, back to the question I had from Abdul Halim. This is an example where you can't, yes, so it would be thermoset, Yasmin. And this is an example where, you know, you can't recycle this in this form. You're completely breaking it down. When you heat up aluminum, it's still aluminum. When you heat up or react this polymer, it's completely broken. Yeah, pretty cool. You can always find fun stuff on YouTube in terms of chemistry videos, I have to say. All right, guys, I think I'll almost be done. I think what I'm going to do is introduce this next section, and then I think next class we'll finish this off, maybe. We'll get pretty close anyways. What time is it? Yeah, 5 o'clock. Yeah, just give me 5 more minutes, and then you can take a break. It's been a long day, I'm sure, for all of you. So there's 2 short sections left. The formation of polymers, and then I think it's chemical reactions, or yeah, this is more of the chemical reactions of polymers. So we're going to look at what are some properties that make polymers commercially, useful in industry. Talk about intermolecular forces, talk about functional groups and things like that. It's a little more complicated than the last section, but it's pretty straightforward. Okay, 3 slides and then I'll stop, okay? That'll be enough for today. So the reason that we have thermoset polymers or thermoplastics, the reason polymers are so different, like a wetsuit is completely different than a PVC pipe, which is completely different from a rubber tire, but they're all polymers. So what makes them different? And a lot of it has to do with the chemicals that are in it. What functional groups are there? And this is related to the attractive forces in those polymer chains. Because these chains can be so long, their forces are really amplified. And what I mean is like they're emphasized. They're a lot bigger than smaller conventional molecules. So the intermolecular forces in, say, well, acetone or ethanol or even, ammonia aren't as prominent, aren't as big as you would see in a polymer. Like, let me just go back. Look at this polymer here. Think, guys, about the intermolecular force. Think about the forces in this molecule. We have like ethers and alcohols, and I mean, it's a crazy molecule. So it can be a little complicated, and luckily for us, we don't really need to get into it too deep. All right, 2 more slides. The large size of polymers, and this just is what I basically said on the last slide, lead to much stronger intermolecular forces. And what this means, if you remember from chemistry 1120, if you have high intermolecular forces, you have higher melting and boiling points. So that's why polymers aren't a gas at room temperature. Polymers aren't typically a liquid at room temperature. You have to heat up polymers, maybe a few hundred degrees to get them to melt. This means they're hard, they can be hard or flexible, but they all have higher melting points than most organic compounds. So compared to like methane or carbon dioxide, the melting points are way higher. When you have a high density polymer, so a straight chain polymer, for example, the intermolecular forces can be even stronger. So high density polymers, where the molecules are so close together, their intermolecular forces are going crazy. Sorry, I got a couple questions here. I'm just reading them, and I got one more slide. I'll answer Harold's first. High intermolecular forces. Yeah, you could say more solid. Now, that's kind of a weird way for me to say that, because it's related to melting point. So high intermolecular forces would be solids at room temperature. I'm not even, don't even like how I said that. Maybe not think about it as more solid, just think higher melting point. So again, that's why polymers you don't typically see as gases or liquids. They're always solids because their melting points are so high. Iman asks a question about page 19. So I'll go back and look at that after. Let me finish this and then I'll answer your question, Iman, because I'd have to go back to that slide. Okay. So intermolecular forces in polymers are typically affected by dipoles. Remember dipoles, polarity. Whoops, I didn't mean to do that. From the monomers that form that polymer. Side groups on the polymer can also affect how they bond and their intermolecular forces. Side groups could be branches or functional groups. So in simple words, intermolecular forces are basically what control the chemical properties of polymers. That's really the big takeaway from this. Intermolecular forces, because the molecules are so complex and so big, really control what type of polymer you have. Is it flexible? Is it hard? Does it melt at 100 degrees? Does it melt at 1,000 degrees? All of these properties are controlled by intermolecular forces. I have one last thing I'll say, and then I'm done teaching. I teach an environmental course, and we do a whole chapter about the chemical properties of water. And I basically tell the students, if you don't know why a chemical does something, it's probably hydrogen bonding. Or for you guys in this course, your answer would be, if you were asked why are the properties of a polymer the way that they are, it's because of intermolecular forces, and that includes polarity and hydrogen bonding. Okay, cool. Now let me check the chat. I'm done. Just let me check the chat. I got to go back to slide 19. Okay, hold on. Boop. Sorry. Okay, let me read that again. Sorry, it's really hard to switch from PowerPoint to chat. I like Zoom, but yeah. So Iman asked, do you need to know these examples? No, you don't need to know this examples. You should know what a homopolymer is. It's a polymer that has one type of monomer. But when it comes to examples, no, I just showed you that picture. Like, you will never have to draw this or look at this or anything like that. Don't worry. But this polymer is made up of one monomer repeated. So it's called homo, which means same. Oh, and back, sorry, page 18. No, you don't need to know these examples. Again, you should know this, but you don't need to know the examples. All right, and it's pretty easy. If you think of the word homopolymer, it's one type of polymer, one monomer. Copolymers, excuse me, think of like cooperation. You're working with different people. Coordinating, working with different people. Co means more than one. I guess they couldn't call it polypolymers, right? Anyways, okay, that was a really bad joke. I'm sorry. All right, guys, that's it for me. I'll see you guys next
Mister,
day. Yes, there's a question.
Can you go back this moment? Few moments.
Yep, to that same slide.
Yes, the last slide.
Okay, hold on. Share. This one?
Otherwise, okay.
Yep. What do you have?
Yes.
Question about this?
Thank you so much.
Oh, that's it. That's all you wanted me to do?
Yeah, I got it. Yeah. Thank you
Okay.
so much.
Okay. Cool.
Thank you.
All right. Thanks, guys. Thanks, everybody.
Mister?
Yes.
How are you? Good?
I'm great. How are you?
I'm good. I want to ask if you can make specifically which part should be studied, like that's which PowerPoint to study.
Yeah. You mean right now or like
in every class, I mean.
Oh, every class? Absolutely. And anytime I say wink, wink, that's definitely something you need to study. And in the classes, I'll try to do more stuff like this with the check marks, so you know what you need to know, or you'll know what you need to study. Don't worry.
Yeah, I mean, like, which PowerPoint should I open? Because I opened it last time, the chemistry.
Mhm.
It was too much information. I didn't know which, what did we take in this class specifically, so I can know.
Yep, absolutely.
Okay, thanks, Mr.
No problem.
Mr.
Yep.
They said in health science the classes will be on campus. Is it? Is the chemistry will be on campus?
No, chemistry is not on campus. Only your labs. Your labs are on campus.
Okay.
Okay.
Thanks.
Perfect.
Sir,
Yep. More questions?
where can I find your office hour?
Okay. Are you Hadil?
Yeah.
Okay, I just saw your message in the chat there. So my schedule changed a lot, but I have it updated. So I do have an answer for you. Don't worry. My office hours, I'll post them on D2L, but actually, I am going to have to post it on D2L because it's going to be on Zoom links. So what I'll do is after this class, like literally right now, I'll make a posting listing my office hours. Is that cool? Is that okay?
All right, sir. Thank you.
Perfect. No problem. All right. I got one more question. Page 36. So Iman, I mentioned this. You don't need to know this. Don't worry. These are just some examples of synthetic polymers. You don't need to study these. Okay, synthetic just means made in a lab. All right, guys, any more questions?
Sir,
Yes?
when we will have like review for the test, or
Yeah, whenever the
Like-
test is, we will do some review.
okay, so you'll post in like D2L like some practice for test, or
The practice is already there. There are worksheets with answer keys in D2L for everything.
Sir, when will it be probably our first test?
First test will be probably around the, I don't want to say a date because I don't know. I have to work with another instructor, but it would be in February, in like the first half of February. And I will give you a week's notice before the first test.
Mr. And it will be in the campus, correct?
The test will be in campus, and we will do some social distancing.
Okay, Mr. Thank you very much.
No problem.
Sir, sorry, last question.
Yeah.
Have you posted the videos for the classes last week?
Yes, I do have them posted, and I can. I've set up a YouTube playlist, so I will post that along with my office hours. It's already been made.
Okay.
I just have to post the link.
Okay, thank you so much, sir. Have a
Thank
great
you.
day.
You too. Thanks. Bye-bye. All right, guys. That's it. I'll see you later. Have a great day. See you soon.
Thank you, Mr. Mark.
Thank you. Have a great day.
You too.